Okay, well, let's look at scenario number 2. Scenario number 2 is that we're going to be looking at the same research study, looking at the relationship between weight gain and blood pressure after switching from second generation. Both, again, were abstracted from the medical record. What is the research question? Well, the research question is the weight change associated with systolic blood pressure change in these patients. So the key thing here is we're looking at numeric data, but we're looking at, in this instance, the same person. So what do? You begin to look at the idea of weight change. And so what do? Well, you look at the weight beforehand, subtract the weight afterwards, and come up with a single number. You look at the blood pressure beforehand and the blood pressure after, subtract them, and you come up with a single number. And so in this instance, then, what you would do is you would correlate the change in weight with the change in blood pressure. You are, in fact, having one measure on a single person on those two variables, the change in the weight and the change in the blood pressure. So in this instance, then, what is the research question, or what is the clinical question? Well, the clinical question for scenario number 2 is the change in weight associated with the change in blood pressure, is that correlation equal or not equal to 0? And that's how it's different from scenario number 1, as we are looking at change from time 1 to time 2 in both of those, versus looking at weight at time 1 with blood pressure at time 1. And therefore, because it is still just a single person measuring their weight, the observations are still independent. Okay, so let's look to see what the correlations are like at two separate points in time. So let's analyze. Let's look at the correlations. Let's look at the bivariate correlations. Okay, so what we're going to look at is the pre-switch weight and the pre-switch systolic blood pressure. And then we're also going to look at the post-switch weight and the post-switch systolic blood pressure to see if both of those are correlated and whether it's correlated higher or lower at what point in time. Let's look at the correlation of the weight to the blood pressure at time 1. So weight to blood pressure at time 1, the correlation is 0.185. And let's look at the weight at time 2, or the post-switch, with the blood pressure at time 2. Well, that's 0.161. In both cases, given almost 1,600 people, the correlation is significant at the rate of 0.01 with a two-tailed test. What else do we expect to see to be highly correlated? Well, we would expect to see weight at time 1 and weight at time 2 to be highly correlated. So the weight at the before the switch and the weight after the switch, whoa! Will you look at that? Almost 0.90. So the weight between time 1 and time 2 is 0.90. Well, let's look at the systolic blood pressure at time 1 and the systolic blood pressure at time 2. Whoa! It's 0.39. So it really is quite a bit different than this 0.90. It's not, the blood pressure evidently really does change between time 1 and time 2 because these correlations are not all that high. The other thing I want you to take a look at is the format of this correlation coefficient, or correlation matrix. This is what they call a correlation matrix. What you see is that the relationship between the pre-switch weight and itself is 1. That's a perfect correlation. And you see that as you go down to this from the upper left to the lower right, that each of these correlations is 1.0. So this is what they call the diagonal. And the diagonal divides in half the lower and the upper part of the correlation matrix. Now, what do you see that is pretty unique about this correlation matrix? Well, you see that the matrix, the value here is 0.185, and here it's 0.185. Here it's 0.167, here it's 0.167, 0.161, 0.61, 0.39, 0.39, and so forth. The correlation matrix is a mirror image of itself on one side or the other. So in many cases what you'll see is a correlation matrix that just has half of the matrix and the other half will be blank. So what you would see in an article is R equals 0.185, P is less than 0.01. Now they won't put a T value in here because they figure that if this correlation coefficient is significant at this level, it's because they use the T critical value to come to this probability in the T distribution, and that you really don't have to have the value of T each time as long as you know that the P value is less than 0.01. So let's go ahead now. What happened is that you have the same person at two different points in time. Well, what happens if in the second question that we looked at earlier is let's look at change and to see how much the change in blood pressure is associated with the change in weight. Okay, well, let's go ahead and look at another example. Let's look at the example of weight change. Now, the other data that we came up with this correlation of 0.75 and the weight between kilograms and systolic blood pressure, that was bogus. That wasn't real. It was something that was made up in a book I got. But now this data that I'm going to be showing you now is the real thing. In this data, what we have is patients that are switched from one second-generation antipsychotic to another. Now, the various antipsychotics have different potentials for metabolic changes. Olanzapine and clozaril have the most change in metabolic parameters such as weight and lipids and so forth. The quetiapine and risperidone historically have been shown to be somewhat intermediate, and the new second-generation antipsychotics, the ziprasidone and aripiprazole, have been shown to have the least amount of impact upon the weight. So what we want to do here is to look to see what the differences were in the association then between weight change and systolic blood pressure. The first thing that I showed you earlier was to do the scatter plot, right? Well, let's go ahead and let's look at our weight change and the systolic blood pressure. Now, let's go ahead and look at these just to start with. Let's look at the frequencies of the weight change and the systolic blood pressure. So change in weight from a 1-year period of time and a change in systolic blood pressure. The statistics, let's go ahead and look at quartiles, standard deviation, minimum, maximum, mean score, skewness. Hit the continue button and let's see what we have. Ta-da! Well, change in weight from pre to post, we have 1,483 real people. The average weight change was basically less than a decline of 1 pound over all of them. The change in blood pressure was less than 1 millimeter of mercury, but the standard deviation, as you can see, is huge here, of 21 pounds and almost 20 points of millimeters of mercury. The skewness, if you look at this, minus 0.569, that's a small skewness. It's slightly negatively skewed, but it's still less than 1, and this is less than 1 as well. The minimum, we had one person that lost 213 pounds, another person who gained 96 pounds. We had another person whose blood pressure went down by 74 points, and another person whose blood pressure went up by 118 points. If you look at the 25th, 50th, and 75th percentile, you see that this minus 1 and this minus 0.95 are very close to one another, so the median and the mean are very close. 25% of the study subjects lost 11 pounds or more, and 75% gained 9, almost 10 pounds or more. All right, so let's go ahead then, now that we've got the descriptive statistics, let's go ahead and look at the scatter plot to see whether this appears to be normally distributed, which the first inclination is to say that it is likely, and to get a look at whether we think that the correlation is going to be high, medium, or low. Okay, well, let's look at SPSS again. Here we have graphs. Last time we looked at the analysis. This time we want to draw a graph. So let's look at two. Let's first look at the histograms and then the scatter plots. Remember, the histograms are going to show us whether each individual variable is normally distributed or not. And so let's first look at the change in weight pre to post. And let's display the normal curve on top of it and see what it looks like. So this is what the histogram looks like. As you can see that it does look pretty well normally distributed, that in fact at the point here of 0 weight is where the mode is, and that the rest of them go down on the way out in what looks like a normally distributed way. So the mean is about 0, and if you remember the skewness, it was somewhat less than 0 as well. So now let's go ahead and look at the change in blood pressure pre to post to see if it's nearly equally normally distributed as well. So again, we'll analyze, we'll look at the histogram, only this time we look at change in blood pressure pre to post. What does it look like? Well, see, again, it looks like it's pretty normally distributed as well. So the first condition, what we have done is we have taken a look at the two variables independently, and in both cases then they appear to be pretty well normally distributed. So let's go ahead then and look at next at the scatter plot. And we're going to look at a simple scatter plot, which means that it is not broken up into the 4 quadrants and so forth. So we're going to define this as our x-axis. Let's say our x-axis is going to be change in weight, and our y-axis is going to be change in blood pressure. So let's go ahead and take a look at our scatter plot. Well, as you can see from our scatter plot, pretty much looks like a shotgun blast, most of it here in the middle, but it gets thinner and thinner around the edges. We have a couple of outliers here. This one person who lost 200 pounds, he actually had an increase in blood pressure, but for the most part, people who have no change and have a change in the weight also appear to have a change in the blood pressure. So let's go ahead then and run the analysis and see what the correlation is like. So analyze correlations. Bivariate correlations, we have our change in weight and our blood pressure. We're going to have the Pearson's correlation. It's going to be a two-tailed test. And we've asked it to flag it in some fashion with the significant correlation. And if we look at our correlations, the Pearson's correlation is 0.178, and it is statistically significantly different. As I said, it's a two-tailed test, and it's significant at the level of 1 out of 100 in the two-tailed test. Now, the thing to notice about correlation matrices is that anything associated with itself has a correlation of 1. So what you'll see is the weight change in weight is associated 1-to-1 with the change in weight, and the change in blood pressure is associated 1-to-1 with the change in blood pressure, and that these are both the opposite of one another. So in a correlation matrix, you really only have to look at what they call the numbers either below the diagonal, this is called the diagonal, or the numbers above the diagonal. Otherwise, they're directly the same. So in this instance, the correlation is 0.178, or in an article, you would probably see a correlation rounded off to 0.18. So this is what a correlation coefficient would look like if you were to look at it from the perspective of a person doing the analysis. This here is what you should see in an article. It should say correlation is equal to 0.18, p is less than 0.01. Okay, so let's take a look at a third scenario. And the third scenario is a research study was started to study the association between weight change and change in systolic blood pressure after switching second-generation antipsychotics. So we're looking at basically the same people that we were looking at before. And again, in both cases, the systolic blood pressure and weight change were abstracted from the patient's medical record. But at this time, we're going to ask a second type of a question, and this is where we begin to look at the idea of prediction, and that is, can weight change help us to predict the amount of systolic blood pressure change? Now, we can't really do this with association. And so what we're going to do is we're going to be looking at this in the next lecture when we begin to look at the idea of simple regression, and then look at the relationship then between correlation and simple regression, because as I said earlier, they're very similar, and in the case of a single independent variable and a single dependent variable, they're pretty much the same. So, hey, we'll be looking at this one at the next lecture, so that gives you some sense that we're pretty much nearing the end of this one. But what I'd like to do is to We're going to do a summary of what we went over today. And that is, first of all, to look at the types of variables suitable for an analysis with correlation. So if you look at those flowcharts in Appendix C, what you're seeing with Pearson's correlation is that you have an independent variable and a dependent variable, both measured at the level of numeric data. So for example, you have weight and systolic blood pressure. The other thing that we talked about is the difference between association and prediction, and we did that in an introductory fashion. We'll be doing a little bit more of that in the next group of lectures about simple regression. Third, we looked at the idea of a scatter plot, and we talked about negative correlations and positive correlations and highly associated scatter plots and weak scatter plots and perfect correlations and non-correlations and so forth between these two numeric variables. So you're going to be needing to think especially about whether it's positive or negative correlations. And if one variable goes up, the other one goes down in a negative correlation, and in a positive correlation, when they both go up together in a positive direction, it of course is a positive direction. But don't get confused with the idea of a negative correlation. If they both go down or they both go in a negative direction, and they both go in the same direction, it is still what they call a positive association. So positive association is that they go the same direction, whether it be up or down. And a negative correlation is they go inversely. They go in the opposite direction. The next thing that we did was we tested a hypothesis of an association using the example in the book and using a bogus example that was created, and interpreting those findings in the framework of what is the correlation coefficient, or R, and then how do we test the significance. And here we use the t-test in the same way as we would use it in the t-test in finding a difference between the two means. But here what we did was we tested the hypothesis that the association was 0 versus the hypothesis that the association was not 0. So it wasn't a difference between two means type of a hypothesis, but it was whether something was 0, whether the difference between the mean was 0, or whether the association was 0. So the clinical or the hypothesis is that there is no association, and the the alternative hypothesis is that there is an association. We showed you how to calculate the association in the Pearson's product moment correlation, or R, actually how to calculate the t-test of statistical significance. And we did some real analyses about real people and looked at real associations of about 1,800 veterans, and looking at the association between weight change and blood pressure change. So